Have you ever gazed up at the night sky, at that silent black expanse dusted with the diamond light of distant stars? You feel like you're looking into a realm of eternal peace and quiet. But what if I told you that very recently, a deafening scream echoed from the very heart of our galaxy, a cry that has been waiting for millions of years to be heard? Today, we're taking a journey 26,000 light-years from home to the center of the Milky Way to witness the awakening of an ancient giant, an object long considered dormant, but which suddenly revealed its true nature. What exactly was it? The dying shriek of a consumed star, a signal broadcast into the void, or simply the cosmic sigh of the monster we call a supermassive black hole? Stick with us, and you'll find out why this event drove scientists worldwide to glue themselves to their telescopes and what it might tell us about the fate of our own galaxy. Do you think we are alone in the universe? Perhaps this distant echo from the Milky Way's center is the strangest answer to that question we have ever received. Before we dive into the core of the event, let's adjust our imaginary navigation systems and figure out exactly where we are headed. Imagine our galaxy, the Milky Way, as a massive, shimmering city made up of hundreds of billions of stars. Like any city, it has a center, a bustling, chaotic region, full of dangers and wonders. It's a place where stars are packed so tightly that the night sky would actually shine brighter than our daylight here on Earth. And in the very, very heart of this metropolis, at its central point, sits something extraordinary, not a mayor nor a town square, but an object of colossal mass and gravity. Astronomers call it Sagittarius A-star, SGR A-star for short. It is the supermassive black hole. Not just a hole, but the true gravitational ruler of our galaxy, whose mass exceeds that of our Sun by 4 million times. For a long time, this giant behaved surprisingly quietly. It seemed to slumber peacefully in the center of its kingdom, only occasionally taking lazy bites out of passing gas clouds or unfortunate asteroids. Astronomers dubbed it the sleeping giant. Its activity was so low that it was a mystery in itself. After all, a gravitational feast was happening all around it, immense amounts of stars, dust, and gas. Why wasn't it swallowing everything in sight? But one day, everything changed. Telescopes that had been tracking this quiet corner of the universe for decades, space observatories like Chandra and XMM Newton, registered something truly extraordinary. The sleeping giant didn't just stir, it woke up. Let's transport ourselves now to the Mission Control Center of a major space observatory. Picture a team of astronomers who have spent years, day after day, monitoring a tiny, specific point at the heart of our galaxy. For them, Sagittarius A-star is an old acquaintance. They know its habits, its temperament. They were accustomed to its quiet nature, disturbed only by small, predictable flares. It was like watching a dormant volcano that occasionally lets out a tiny wisp of smoke. But on this particular day, something entirely different materialized on their screens. The data streaming in from the X-ray telescopes suddenly showed a sharp, unimaginable spike in brightness. This wasn't a wisp of smoke, this was a full-blown eruption. The level of X-ray radiation emanating from the immediate vicinity of the black hole had jumped hundreds of times above its normal background level. Imagine listening to quiet, soothing background music, and then, without warning, the deafening roar of a jet engine explodes right next to your ear. Shock, bewilderment, and then a frantic burst of activity. Scientists worldwide began double and triple checking the data. Could it be an equipment malfunction, a calibration error, a random cosmic ray hitting the detector? But no, different telescopes, positioned at various points in orbit around Earth, independently confirmed the same phenomenon. Something enormous was happening at the core of the Milky Way. It was as if a lighthouse, which usually emitted a faint glimmer once an hour, had suddenly flared up with the intensity of a searchlight, momentarily blinding the observers. The initial reaction was a mixture of elation and apprehension. Elation because the astronomers were witnessing a unique, possibly once-in-a-century event. Apprehension because nobody knew what it truly signified. Was this a one-off occurrence, or was the giant truly waking up for good? What triggered such a dramatic shift? This marked the beginning of one of the most intriguing astrophysical detective stories of our time, and the first order of business was to meticulously study the voice of this cosmic scream, the signal itself. Once the initial shock wore off, the meticulous analysis began. What exactly was this scream emanating from the galactic core? The signal, or in scientific terms the flare's light curve, was akin to a dramatic piece of music. It didn't just flash on and disappear. It had a distinct structure, an overture, a blinding climax, and a long, drawn-out decay. The intensity surged rapidly, reached an astonishing peak that stunned astronomers, and then gradually, over the course of several hours, began to subside. This wasn't a simple bang, this was a complex, time-stretched event. Astronomers immediately compared this new flare to every previous outburst ever registered from Sagittarius A-star. The result was staggering. This new eruption was hundreds of times more powerful than the brightest flare they had ever witnessed before. It was like comparing the snap of a firecracker to the thunder of an artillery barrage. But sheer brightness wasn't the only takeaway. A crucial element of the analysis was the emission spectrum. To put it simply, scientists broke down this X-ray light into its constituent colors to map its composition and origin, and the spectrum revealed that the source of this radiation was matter heated to unbelievable temperatures, tens of millions of degrees. It was superheated plasma whirling around the black hole at speeds approaching that of light, just before being consumed forever. Picture water swirling down a drain in a vortex. Now, instead of water, substitute superheated ionized gas. And instead of a simple drain, substitute an object with gravity so extreme that not even light can escape. It is the friction within this furious, spiraling dance of matter, what scientists call the accretion disk, that generates this immensely powerful X-ray emission. This flare was definitive proof that the black hole had just indulged in a substantial meal. Now the key question facing researchers was, what exactly was it? What kind of fuel could possibly trigger such a colossal cosmic fireworks display? Unraveling this mystery promises to reveal not only the black hole's diet, but also the fundamental processes that govern life and death at the very heart of our galaxy. So, who is the prime suspect in this cosmic crime? Naturally, the ruler of this domain, Sagittarius A-star itself. But why Escar A-star? Let's dive into the physics of what's happening. Black holes are inherently invisible. They don't emit light. Quite the opposite. They consume it entirely. We can only detect them through indirect evidence, by observing how their monstrous gravity distorts surrounding space and influences nearby matter. The most telling sign is the accretion disk. Picture a massive cosmic whirlpool. Anything that wanders too close to a black hole, stars, gas, dust, doesn't fall straight into the abyss. Instead, it gets captured by the immense gravitational pull and spirals inward, forming a thin, intensely heated disk. The material within this disk moves at mind-boggling speeds. Crucially, the inner layers spin faster than the outer ones. This differential speed generates colossal friction. Gas particles collide and grind against each other, heating them up to millions, perhaps even billions of degrees. This superheated matter, now turned into plasma, begins to glow fiercely, particularly in the X-ray and gamma-ray spectra. This brilliant light is the death shriek of matter moments before it crosses the event horizon and vanishes from our universe forever. So, when we observe a sudden flare emanating from the galactic center, we are not seeing the black hole itself, but rather the evidence of its latest feast. The more material a black hole consumes, the brighter the accretion disk shines. Normal, minor flares are caused by small clumps of gas, or maybe stray asteroids tumbling in. However, a flare of the magnitude observed by astronomers suggested that Sagittarius A-star had just devoured something truly substantial for lunch. This event offered direct proof that the process of accretion, that is, the consumption of matter, is not a constant, smooth flow. Instead, it can be impulsive and explosive. The sleeping giant didn't just wake up, it threw a veritable feast, and astronomers worldwide received a front-row invitation to witness this massive spectacle. The only thing left to determine was what exactly had been on the menu. The detective investigation continues. We have the crime scene, the immediate vicinity of Sagittarius A-star. We have the fingerprints, the unique light curve and spectrum of the flare. Now we need the body, the celestial object that was swallowed and caused all the commotion. What could it have been? Scientists started sifting through the possibilities, much like detectives interviewing witnesses. The first and most obvious candidate was a star. There are countless stars orbiting the galactic center black hole on elongated paths, and it's entirely possible that one of them strayed too close. When a star enters the black hole's tidal zone, it gets ripped apart. This process is known as a tidal disruption event, or TDE. Imagine stretching a piece of putty. The side closer to your hand stretches harder. Gravity works the same way. The side of the star closest to the black hole is pulled significantly harder than the far side, and the star simply can't withstand that difference in force. It is torn into long streams of gas, some of which fly away while the rest plunges toward the black hole, causing a massive flare. It's an elegant and logical theory. However, calculations quickly showed that the observed flare was too short and sharp for a classic stellar TDE. Such an event typically lasts months or even years, yet the flare we observed subsided within just a few hours. This meant either the culprit was an extremely small and compact star, or the theory was wrong. The next candidate on the list was a large gas and dust cloud. Plenty of these orbit the galactic center as well. A cloud falling onto the accretion disk could cause a sudden density increase in the matter there, leading to a dramatic spike in brightness. This version perfectly explained the relatively short duration of the flare. Intriguingly, astronomers had already been tracking an object called G2 for several years. This dense gas cloud passed dangerously close to Sagittarius A-star back in 2014. Everyone had been waiting for fireworks then, but nothing spectacular happened. Could this be a delayed reaction? Perhaps some of G2's material only just now reached the accretion disk, triggering the flash. This became a very popular hypothesis. Finally, more exotic options were considered, such as the impact of a large asteroid or comet. An object spanning several tens of kilometers composed of rock and ice could certainly generate enough energy upon impact. This would explain both the brevity and the sheer power of the flare. Each of these theories had pros and cons, and to determine the correct culprit, scientists needed more evidence. To push their investigation forward, astronomers needed a clever technique, something we can call cosmic echolocation. This involves the phenomenon known as a light echo. What exactly is that? Imagine you're in a massive cave and you shout loudly. First, you hear your own voice, and then after a short delay, reflections of that sound bounce back to you from the cave walls. By analyzing the delay and the nature of the echo, you can determine the size and shape of the cave, even if you can't see it. The exact same principle applies to light. When a powerful flare erupted from the galactic center, its light, or in this specific case, X-ray radiation, raced outwards in all directions at the speed of light. Some of that radiation came directly to Earth, which is what we registered as the flare itself. But surrounding Sagittarius A-star are vast numbers of molecular clouds, gigantic, cold clumps of gas and dust. When the radiation front from the flare hits one of these clouds, it illuminates it, causing it to fluoresce, much like UV light makes white clothes glow in a nightclub. This reflected, or more accurately re-emitted glow, is the light echo. Because the light requires extra time to travel from the black hole to the cloud, and then from the cloud back to us, we observe this echo significantly delayed. By studying these echoes, scientists can achieve remarkable things. Firstly, they can pinpoint exactly when the flare occurred and how powerful it was, even if they missed the original event entirely. It's like reconstructing a crime scene from the residual evidence left behind. Secondly, by watching the light echo propagate across various clouds, they can create a three-dimensional map of their structure and location. This is precisely like using sound echoes to map that invisible cave. And most critically in this investigation, analyzing the echo's spectrum reveals the characteristics of the original radiation. This allows astronomers to reconstruct the flare's properties with incredible precision. Astronomers aimed their X-ray telescopes at known molecular clouds near the galactic center and waited, and they were rewarded. Clouds that had previously been dark and cold began to glow, one after another, in the X-ray spectrum. This was irrefutable proof that they had been illuminated by a massive flare emanating from the core. The picture became clearer. The light echo not only confirmed the black hole's grand feast, but also handed scientists a powerful new tool for studying its consequences and potentially for peering directly into the galaxy's past. The study of light echoes led to an even more astonishing discovery. It turns out our so-called sleeping giant isn't really dormant at all. Instead, it behaves more like a predator that can lie in wait for a long time, but which was incredibly active in the past. For years, astronomers had noticed a strange phenomenon. Molecular clouds located far from Sagittarius A-star were glowing faintly in X-rays, even though there was no visible source nearby. No hot young stars or supernova remnants were close enough to heat them up. This was a long-standing mystery. Now, thanks to the study of light echoes from the recent flare, everything makes sense. Scientists realized that this faint, ghostly glow coming from the distant clouds is also an echo, but from much older and more powerful events. In fact, we are seeing reflections of eruptions that occurred hundreds, perhaps even thousands of years ago. The light from those ancient flares passed Earth long ago, before we even had X-ray telescopes to detect it. But it is only now reaching these distant clouds and causing them to illuminate. It's like finding detailed frescoes in an old, quiet castle, depicting scenes of wild feasts and realizing that this abandoned, silent residence was once the center of a bustling, active life. Therefore, the recent awakening isn't an anomaly. On the contrary, it might actually be a return to the norm. It appears that SGR A-star was far more voracious in the past. Periods of intense activity where it devoured vast amounts of matter and shone millions of times brighter in X-rays than it does today were followed by periods of dormancy. We happen to be living in one of those quiet stretches. But this silence is deceptive. The galactic center is a dynamic, constantly changing environment. And the recent flare is a stark reminder of the colossal power that lies dormant in the heart of the Milky Way. We didn't just witness a flare, we saw an echo of our galaxy's deep past, and perhaps a glimpse into its future. This discovery forces us to fundamentally reevaluate how galaxies evolve It turns out that central black holes don't just passively accumulate mass. Their activity is cyclical, and these cycles can profoundly influence the entire galaxy. The evidence of Sagittarius A-star's tumultuous past goes far beyond mere light echoes. We have much larger, more massive structures that point to truly cataclysmic events having occurred right at the heart of our galaxy. Imagine lifting your perspective high above the Milky Way's disk, viewing it edge-on. If we had the ability to see in gamma rays, the sight would be astonishing. Two gigantic bubbles stretch out from the galactic center, perpendicular to its disk, extending both up and down. They are called the Fermi Bubbles, named after the Fermi Gamma-ray Space Telescope, which discovered them back in 2010. These structures are colossal. Each one stretches 25,000 light-years away from the galactic plane. Together, they form a shape resembling an hourglass or a figure eight, reaching a total height of 50,000 light-years. That's nearly half the diameter of the entire Milky Way. So what exactly are these bubbles? They are vast regions filled with superheated gas and high-energy particles, all intensely emitting gamma radiation. While their origin was long debated, the consensus among scientists today is that they are relics left behind by one or more immense energy outbursts from the galactic center. According to the leading hypothesis, several million years ago, Sagittarius A-star underwent a period of extraordinarily high activity. It may have swallowed an entire star cluster or a gigantic molecular cloud. This process wasn't just accompanied by the bright illumination of the accretion disk. It led to the formation of relativistic jets, narrow streams of plasma shooting out from the black hole's poles at near the speed of light. These jets, acting like gigantic cosmic blowtorches, pierced the galactic disk and inflated these enormous bubbles into the surrounding intergalactic medium. The energy contained within them is equivalent to hundreds of thousands of exploding supernovae. This event must have been one of the most tremendous in the history of our galaxy. Now, returning to the recent flare we discussed, we must ask, is this tiny, almost imperceptible tremor merely an aftershock, an echo of those titanic past events? Perhaps we aren't just witnessing an awakening, but a subtle reminder of the true potential of our sleeping giant. The Fermi Bubbles are scars on the body of our galaxy, and our recent flare is nothing more than a small spark set against the backdrop of that ancient cosmic fire. Science thrives on constant doubt and the relentless search for alternatives. Therefore, while the theory that the black hole simply had a cosmic lunch remains the leading hypothesis, scientists are mandated to explore every other possibility, no matter how exotic. What if Sagittarius A-star isn't the culprit? What else could have caused such a powerful, rapid flash right in the heart of our galaxy? One leading alternative is a magnetar flare. Magnetars are a unique type of neutron star defined by magnetic fields that are quadrillions of times stronger than Earth's, fields that push the limits of physics. Occasionally, the crust of these stars experiences starquakes. These seismic events cause the magnetic field lines to violently snap and realign, releasing colossal amounts of energy in the form of gamma and X-rays. Such bursts are incredibly powerful and short-lived, which aligns well with our observations. The catch with the magnetar hypothesis is that it requires the star to be positioned incredibly close to Sagittarius A-star, yet somehow avoid being swallowed by it. This demands a very specific and unlikely cosmic alignment, making the scenario improbable, but definitely not impossible. Another, perhaps even more intriguing theory bypasses the idea of the black hole consuming a typical object and suggests something far more exotic. For instance, what if the flare was caused by the tidal disruption of a compact object, not a normal star, but perhaps a white dwarf or even a neutron star. These objects are vastly more compact and dense. Their destruction would occur much closer to the event horizon, resulting in a quicker, far more energy-intensive process that aligns better with the short duration of the observed flash. Or consider a violent collision between two compact objects, like two neutron stars, happening in the immediate vicinity of the central black hole. Such an event would generate not only a powerful X-ray flare, but also detectable gravitational waves. Unfortunately, our current gravitational wave detectors are not sensitive enough to register such an event occurring 26,000 light-years away. Finally, we arrive at the truly speculative hypotheses. These include the black hole consuming a clump of dark matter, or perhaps even a primordial black hole, a hypothetical object formed moments after the Big Bang. Considering these alternatives is more than just an intellectual exercise. It is a vital component of the scientific method, pushing researchers to seek new evidence and develop more refined models. Although currently all the forensic evidence points toward Sagittarius A-star enjoying a cosmic feast, science always leaves the door open for the universe to surprise us. All right, the giant at the heart of our galaxy has woken up and had a little snack. But why should we care? We're a comfortable 26,000 light-years away, right? Actually, the central black hole's activity is immensely important for the entire galaxy, including our quiet corner of the cosmos. Galaxies whose central black holes are actively consuming matter and shining brightly are known as active galactic nuclei, or AGN for short. The most powerful among them, quasars, can shine brighter than all the stars in their host galaxy combined. Currently, our Milky Way is not considered an active galaxy, but as we've discovered, it might well have been one in the past, and that radically changes the picture of its evolution. How exactly does an active nucleus influence its galaxy? There are two primary mechanisms that work in opposing directions. This whole process is called feedback. On one hand, the powerful radiation and jets erupting from the black hole's vicinity can stimulate star formation. Imagine a giant shockwave radiating outwards from the galactic center. As it travels through molecular clouds, it compresses and densifies the gas, essentially nudging it toward collapse and the formation of new stars. In this scenario, the active nucleus acts as a cosmic midwife, assisting in the birth of new generations of suns. But there is a flip side to the coin. If the nucleus's activity is too intense, that very same process can have the opposite effect. Powerful winds and radiation might not compress the gas. Instead, they can blow out the gas from the galaxy, stripping it away into intergalactic space. They superheat the remaining gas to temperatures so high that it can no longer condense and form stars. In this case, the active nucleus acts as a sterilizing factor, shutting down star formation and essentially condemning the galaxy to a slow fade. It transforms into a red and dead elliptical galaxy, populated only by aging stars. Which of these two processes prevails depends on a multitude of factors: the black hole's mass, the rate of accretion, and the overall gas supply in the galaxy. By studying the recent outburst of Sagittarius A-star, we gain a unique, real-time opportunity to observe this feedback mechanism at work, even if only on a miniature scale. We are witnessing how the awakening of this central monster influences its immediate surroundings, and this helps us understand how similar but far more powerful past events shaped the Milky Way into the galaxy we know today. So, the cosmic detective story is reaching its climax. We've witnessed a unique event, analyzed the clues, and explored various theories. What comes next? What are the next steps in this thrilling investigation? First and foremost, astronomers worldwide are maintaining continuous monitoring of the galactic center. it's safe to say that Sagittarius A-star, or Sgr A-star, is currently under the most intense scrutiny in human history. Dozens of telescopes, both earthbound and space-based, operating across the entire electromagnetic spectrum, from radio waves to gamma rays, are focused on this single point. Scientists are hoping to catch the next flare. If this wasn't a one-off event but the beginning of a new period of activity, then repeat flares are inevitable, and every new flare will provide invaluable data. By comparing them, we can determine exactly what the black hole is consuming, how its accretion disk is structured, and what physical processes are taking place there. Special hopes are being placed on new instruments currently coming online, such as the James Webb Space Telescope. Observing in the infrared, JWST can pierce through the dense dust clouds that obscure the galactic center in visible light. With its help, we can pinpoint stars and gas clouds in the black hole's immediate vicinity and perhaps even spot the very object that is about to become its next meal. Another crucial direction involves the further study of light echoes. By observing how the light from the flare continues to spread out and illuminate new clouds, scientists will be able to create an even more detailed three-dimensional map of the galaxy's central region. This will not only help us understand the structure of this complex area, but also better reconstruct the history of Sgr A-star activity over the past millennia. We truly live in an amazing time. Technology has advanced to the point where we can observe in real time the processes unfolding at the very heart of our stellar home. Every new observation, every new flare, is another page in the Milky Way's history book that we are learning to read. And who knows what other surprises await us from this ancient giant, which seems to be just now waking up from a long slumber. Let's momentarily step away from X-rays and gamma-ray bursts and talk about gravity. A black hole, after all, is fundamentally an object defined by its gravitational field, and it is the study of gravitational effects at the galactic center that gives us the most precise data about Sagittarius A-star itself. For more than 20 years, teams of astronomers led by Reinhard Genzel and Andrea Ghez have conducted meticulous work. They have observed the movement of individual stars orbiting the invisible center of the galaxy. These stars, known as S-stars, follow highly eccentric elliptical orbits at enormous speeds. For instance, the S2 star completes one full circuit around the black hole in just 16 years, accelerating at its closest point to speeds reaching several % of the speed of light. That's simply incredible. Imagine a solar mass object flying through space at over 7,000 kilometers per second. By monitoring the orbits of these stars, scientists achieved what once seemed impossible. They managed to weigh the central black hole. It is thanks to these observations that we know its mass is approximately 4 million times the mass of the Sun. Moreover, these stars are perfect probes for testing Einstein's general theory of relativity under conditions of extreme gravity. For example, when the S2 star passed its pericenter, the point closest to the black hole in its orbit, in 2018, astronomers detected the gravitational redshift effect predicted by Einstein. The light emitted by the star reddened, meaning its wavelength increased, because it had to overcome that immensely powerful gravitational field. This was yet another brilliant confirmation of the theory of relativity. Now let's return to our flare. How is it connected to these stars? It's quite simple. If the flare was caused by some object falling in, that object was likely part of the same population as the S-stars. Perhaps it was a star whose orbit had become too unstable, or a gas cloud stripped away from one of those stars. Thus, studying stellar orbits and studying accretion flares are two sides of the same coin. They complement each other, providing us with a complete three-dimensional picture of what is happening in this amazing and extreme location, the very heart of the Milky Way. This is a wonderful example of how diverse research methods in astronomy combine to solve one major cosmic mystery. Beyond X-ray and infrared observations, radio telescopes play a crucial role in studying the galactic center. This brings us to one of the most ambitious scientific endeavors in history, the Event Horizon Telescope, or EHT. It's not a single telescope, but a global network of radio dishes scattered across the entire planet, stretching from Hawaii all the way to Antarctica. By working in unison, they create a virtual telescope the size of the Earth, a technique known as Very Long Baseline Interferometry, or VLBI. The resolving power of this kind of telescope is simply astonishing. It's sharp enough that if you were using it, you could read a newspaper headline lying on the surface of the Moon, all the way from Earth. And the main goal of this entire project is to obtain a direct image of a black hole's shadow. In 2019, the EHT team presented the world with the first ever image of a black hole shadow located in the center of the M87 galaxy. It appeared as an orange ring of fire, a luminous accretion disk with a dark void at its center. This dark region is the shadow cast by the event horizon itself. Then in 2022, the photograph of our own Sagittarius A-star was finally published. It looked remarkably similar to its older sister. In M87, the same glowing ring, the same central dark region. However, capturing this image was a far more challenging task. Sagittarius A-star is much smaller and lighter, meaning the matter orbiting it moves significantly faster. The appearance of Esca A-star changes literally within minutes, whereas in M87, changes happen over days or weeks. It's the equivalent of trying to photograph a running cheetah instead of a sleeping lion. Now imagine what would happen if we aimed the Event Horizon Telescope at Sagittarius A-star during one of the powerful flares we've been discussing. We would be able to see in real time how the structure of the accretion disk changes, how matter spirals into it, and how hotspots of plasma form. We would witness the dance of matter on the edge of the abyss. This wouldn't just be a light curve or a spectrum, it would be a movie filmed right at the edge of the universe. Coordinating the EHT's work with X-ray and other telescopes is one of the key objectives of modern astrophysics. Every new flare from our central giant offers a unique chance to launch this complex machine and gather data that could revolutionize our understanding of black hole physics. We often talk about black holes eating stars or gas clouds, but what truly happens to that matter as it approaches the event horizon? The actual process is far more complex and fascinating than simply falling into the void. Let's picture a star that carelessly wandered too close to Sagittarius A-star. As we've discussed, tidal forces rip it apart, but what happens to that material after the destruction? It doesn't instantly plummet into the black hole. Instead, it forms that familiar structure, the accretion disk. This disk, however, is far from uniform. The material within it doesn't move in ideal, smooth, circular orbits. It experiences intense turbulence, generating shock waves. Magnetic fields twist and reconnect, sparking powerful flares. It's akin to a boiling cauldron where matter is superheated to unimaginable temperatures. The physics of accretion disks is truly one of the most challenging frontiers in modern astrophysics. Scientists build incredibly complex computer models just to attempt to reproduce the processes occurring within them. This is why the recent flare observed from Sagittarius A-star is a priceless gift to theorists. They can finally compare their models against real-world observations. For instance, the shape of the light curve, a rapid rise followed by a slower decay, reveals how viscosity and magnetic fields within the disk force the material to spiral gradually toward the center. The spectrum of the radiation, meanwhile, informs us about the temperature and density of the plasma at various distances from the black hole. Furthermore, we often detect polarization in the light coming from the accretion disk. This means the light waves oscillate predominantly in a single plane. Analyzing this polarization provides crucial information about the geometry and strength of the magnetic fields near the black hole. After all, it is these very magnetic fields that play a critical role in launching the jets, those powerful streams of matter that erupt from the poles of some black holes. While Sagittarius A-star hasn't shown powerful continuous jets yet, some data hints at the existence of weaker, intermittent outbursts. Perhaps the recent flare was directly related to the brief launching of just such a mini-jet. Thus, a single event, a powerful flare, allows us to test and refine dozens of theoretical models that describe the most extreme physical processes in the universe. It's like running a unique lab experiment, except the cosmos itself is our laboratory, and the equipment is a gigantic black hole. Let's take another look at the Fermi Bubbles. We've discussed them as the lasting scars of ancient activity from Sagittarius A-star, but that's only half the story. Recent observations, particularly those conducted by other telescopes like the Emitted X-ray Observatory, have revealed a much more dramatic picture. It turns out that the gamma-ray Fermi bubbles are actually nested within even larger structures that glow brightly in the X-ray spectrum. These X-ray structures, aptly named the Emitted bubbles, extend much farther into space, almost reaching our neighboring galaxy, the Large Magellanic Cloud. They stand approximately 80,000 light-years tall. This staggering size implies that the energy released by the event that created them was far greater than previously estimated. It even suggests the possibility that these weren't just one event, but two different outbursts separated by time. First, a more powerful initial eruption created the enormous X-ray bubbles, and then, inside those structures, a later and slightly less powerful outburst inflated the gamma-ray Fermi bubbles. This Russian doll arrangement indicates that the central black hole's activity isn't a chaotic mess, but perhaps a series of repetitive cycles. Studying the chemical composition of the gas within these bubbles provides even more crucial clues. For instance, if they had been created not by the black hole's activity, but by a massive star formation burst at the galactic center, which was one of the alternative theories, the gas would be enriched with heavy elements, the material forged deep inside stars and scattered during supernova explosions. However, observations show that the gas there is relatively clean, which strongly supports the scenario of ejections originating from the black hole's accretion disk. What does any of this have to do with the recent flare we're observing now? Everything. By watching this tiny spark today, we gain a unique opportunity to understand the physics driving the processes that led to such titanic consequences in the past. It's like studying a small firework to understand how a nuclear bomb works. The principles are the same, only the scales are different. Every new observation of Sagittarius A-star helps us write another chapter in the epic story of how our galaxy and its central monster interacted over billions of years, ultimately shaping the world we see today. When we talk about the activity of Sagittarius A-star, SGR-A-star, one of the most intriguing aspects is the question of timing. Whenever we observe the galactic center, we must always remember that we are seeing it as it was 26,000 years ago. That's how long it takes for light to travel the distance between the center and us. How this means the flare we detect today actually occurred during an epoch when mammoths still roamed the earth and our ancestors were drawing on cave walls. This naturally creates a bit of a philosophical paradox. Right now, this very second, something even more dramatic might be happening at the core of our galaxy, but we won't learn about it for another 26 millennia. We are perpetually looking into the past. However, this very time delay effect can actually be used to our advantage. As we've discussed, light echoes from those flares, reflected off surrounding molecular clouds, reach us late. This delay depends on how much farther away the cloud is compared to the direct path the light takes from the galactic center. By studying clouds situated at different depths or distances, we can essentially build a chronology of SGR A-star's activity over the past few hundred or even thousands of years. It's similar to how geologists study rock strata to reconstruct the Earth's history. Every layer records a specific epoch. In our case, every illuminated cloud records a flare that occurred at a specific moment in the past. Some research based on this method suggests that approximately 300 Earth years ago, which corresponds to 26,300 years ago in the galactic center's timeline, SGR A-star experienced another massive outburst, possibly even more powerful than the one we are currently discussing. Intriguingly, this timing roughly coincides with 17th century observations by Japanese and Korean astronomers who recorded a guest star in the constellation Sagittarius. Could they have seen the optical manifestation of this event? It's currently just a hypothesis, but it certainly captures the imagination. Thus, the center of our galaxy is more than just a location. It's a time machine allowing us to peer into the past and reconstruct the history of our cosmic home. Whenever we talk about black holes, one question always pops up. Are they actually a threat to us? Could Sagittarius A-star ever swallow the solar system? I hasten to reassure you, in the foreseeable future, no, there is absolutely zero danger. We are 26,000 light-years away, nestled on the quiet, calm outskirts of our galactic metropolis. For the black hole to swallow us, the entire solar system would have to drastically change its orbit and undertake a long, highly improbable journey toward the center. The gravitational influence of Sagittarius A-star at this distance is negligible. We orbit the galactic center of mass, not the black hole itself. However, this doesn't mean its activity cannot affect us indirectly. If Sagittarius A-star enters a phase of extremely high activity comparable to a quasar, it will become a source of incredibly powerful radiation. Torrents of X-rays, gamma rays, and high-energy particles would stream out in all directions. Even at our distance, this radiation could have serious consequences. For instance, it could severely damage Earth's ozone layer, leading to a massive increase in surface ultraviolet radiation. This, in turn, would negatively impact the biosphere and could potentially trigger a mass extinction event. Furthermore, a powerful flood of cosmic rays would boost background radiation levels, posing a threat to all life and especially to satellites and astronauts in orbit. However, it's crucial to understand that we are talking about events of truly apocalyptic scale, which are exceedingly rare. The activity of Sagittarius A-star would need to increase millions, if not billions, of times beyond what we currently observe. Most astronomers agree that nothing of the sort is expected for the next few million years. Our galaxy simply doesn't have enough fuel, free gas, in the central regions left to sustain such monstrous activity, so we can sleep soundly. But the recent flare-up serves as a powerful reminder that the universe is not a static or entirely safe place. Forces lie dormant within it that make all our terrestrial weaponry seem like mere children's toys. By studying these forces, we not only satisfy our curiosity but also gain a better understanding of our place in this vast and sometimes dangerous cosmos. Let's go back to the G2 object we mentioned earlier. This story deserves its own segment because it perfectly illustrates how science works, a cycle of high expectations, profound disappointments, and unexpected discoveries. Back in the early 2000s, astronomers spotted a small, compact object traveling along a highly elongated orbit, leading it straight toward Sagittarius A-star. Spectral analysis suggested it was likely a cloud of gas and dust, roughly 3 times the mass of Earth. They named it G2. Scientists calculated its trajectory and realized that in 2014 it would pass closer to the black hole than any object previously observed, just a few hundred astronomical units away. The astronomical community held its breath. Everyone was anticipating a spectacular show. The expectation was that the black hole's immense tidal forces would rip the cloud apart, and as its materials spiraled inward, it would trigger a massive, months-long flare. Telescopes around the world were primed and ready. However, 2014 came and went, and the predicted fireworks never materialized. Sagittarius A-star remained surprisingly calm, showing only a slight uptick in activity. This event was quickly dubbed a cosmic dud. The disappointment was palpable, but it forced scientists to rethink their hypotheses. Why wasn't the cloud torn apart? One leading theory suggests G2 isn't just a gas cloud. It might be hiding a dense star at its core, enveloped by a thick, gaseous shell. The star's own gravity would have been enough to hold the cloud together, preventing its complete annihilation. Another theory proposes the cloud was simply much denser than initially estimated, allowing it to pass through the danger zone with minimal loss. Now, in light of a new, much more powerful flare that occurred several years later, the G2 hypothesis is back on the table. What if that was a delayed reaction? Perhaps some of the material was stripped away from the cloud, but it took several years for that material to spiral inward, finally reaching the inner edge of the accretion disk and triggering the big eruption. This would explain both the delay and the sheer power of the event. The G2 story is a classic cautionary tale that the cosmos rarely meets our expectations, but it is precisely in these scientific failures and anomalies that new knowledge and more refined theories are born. We often talk about the center of the galaxy, but what is that place actually like? It's much more than just a dot on a map. It's an entire ecosystem governed by its own extreme laws. The central parsec of the Milky Way, an area only about 3 light-years in diameter, is one of the most densely populated and chaotic places in the entire galaxy. The stellar density here is 1,000,000 times higher than in the Sun's neighborhood. If we lived on a planet in this region, the night sky would be blindingly bright from the light of millions of nearby stars. However, life there would be impossible. The radiation levels from the stars and the black hole itself are lethal. Furthermore, the stars here move at tremendous velocities, and collisions between them are not uncommon events. Aside from the old stars, there is also a significant population of young stars. This in itself is a profound puzzle known as the paradox of youth. Theory suggests that the black hole's powerful tidal forces should have prevented new stars from forming out of gas clouds. Yet, they are undeniably present. Perhaps they formed elsewhere and migrated toward the center, or maybe the process of star formation in these extreme conditions follows a scenario we don't yet understand. The entire region is permeated by powerful magnetic fields that form complex structures of filaments and arcs. Hot gas flows along these lines, creating a visual display similar to the Sun's corona, but scaled up to galactic proportions. And in the midst of all this chaos sits Sagittarius A-star, whose gravity directs this entire complex orchestra. When we observe a flare, we are witnessing just one act in this grand cosmic drama. This flare results from the black hole interacting with one of the countless objects that populate this turbulent region. It might be a star ripped from its orbit by a gravitational disturbance from another star. It could also be a clump of gas blown away by the stellar wind from one of the massive young stars. Understanding this complex ecosystem is the key to knowing why Sagittarius A-star behaves the way it does. And every flare, every new observable phenomenon is another piece of the puzzle that helps us build a complete picture of this astonishing and still largely mysterious world. Let's talk about the future. And I don't mean just future observations, but the future of Sagittarius A-star itself and the destiny of our entire galaxy. Black holes, despite their reputation, are not immortal. Stephen Hawking's theory suggests that they slowly evaporate due to a quantum effect known as Hawking radiation. However, this process is so agonizingly slow that for a supermassive black hole like Sagittarius A-star, the time scale involved is vastly, vastly longer than the current age of the universe. So in that sense, we have nothing to worry about. But its activity will change in the future. In about 4.5 billion years, a truly momentous event awaits our Milky Way galaxy. A collision with our neighboring galaxy, Andromeda. This will be a slow, yet inevitable process that will unfold over hundreds of millions of years. This merger will see the two spiral galaxies transform into a single, giant elliptical galaxy, the one astronomers jokingly call Milky Way. During this cosmic convergence, huge amounts of gas and dust from both galaxies will rush towards the center of the newly merged structure. This will be an absolute feast for the central black holes. First, Andromeda's supermassive black hole and our own Sagittarius A-star will spiral around each other, eventually merging into one single, even more massive, black hole. This process will be accompanied by a colossal release of energy, including a tremendous burst of gravitational waves. The resulting unified cosmic monster, having received an immense supply of fuel, will enter a phase of tremendously high activity. For several million years, Milky Way will become a blazing quasar, visible from all corners of the observable universe. This will be a truly majestic and terrifying spectacle. Of course, humanity will most likely be long gone by then, and our own sun will have already swollen into a red giant. But the very idea that we can predict such monumental cosmic events scheduled to happen in the unimaginably distant future is absolutely mind-boggling. By studying a small, unassuming flare that happened yesterday, we are essentially learning to read the history book of our entire galaxy's future. We've explored countless facets of this incredible event, tracing its path from the moment it was first detected to its profound galactic-scale consequences. Yet beneath all the complex theories and rigorous observations lies something fundamentally simple and deeply human: curiosity. Why are we so invested in phenomena happening 26,000 light-years away? Why do thousands of scientists worldwide dedicate their lives to studying these remote, seemingly abstract occurrences? I believe the answer is woven into the very fabric of who we are. We are creatures perpetually looking up, gazing into the heavens and asking questions. What is out there? How does it work? Are we alone? The exploration of the cosmos isn't just a quest for new knowledge. It is a search for ourselves, for our true place in this immense and incomprehensible universe. Every new discovery, be it an exoplanet orbiting a distant star or a flare from a central black hole, expands the horizons of our understanding. It shows us how intricate, how beautiful, and occasionally how dangerous the universe truly is. The event we've been discussing today is a perfect illustration of the scientific process. It began with a single anomalous signal, just numbers flickering on a computer screen. But hidden behind those digits was an entire cosmic narrative, a story of gravity, of matter in extreme states, and of the past and future of our galaxy. Deciphering that story required the collaborative effort of hundreds of people, utilizing dozens of the most complex instruments ever built, the absolute pinnacle of our technological achievement. This flare is more than just an astronomical phenomenon. It is a profound challenge to our intellect. It is a cosmic riddle thrown down by the universe itself. And in the process of solving this riddle, we don't just learn more about the cosmos, we become better versions of ourselves. We learn to collaborate, to share knowledge, to doubt our initial conclusions, and to pursue the truth, no matter how unexpected it may be. As long as this thirst for knowledge remains alive within us, we will continue to look up, anticipating new signals, new mysteries, and the fresh discoveries that await us in the silent depths of space. When we consider events on such a massive scale, it's easy to overlook the fact that everything we see is governed by the fundamental laws of physics. The waking up, or flaring, of Sagittarius A-star isn't magic. It's a demonstration of how nature operates under the most extreme conditions imaginable. Underlying all of this is Einstein's general theory of relativity, which treats gravity as the curvature of space-time. A black hole represents the point where this curvature becomes infinite. Gravity, however, is merely the stage set. The leading actors are matter and energy, and their complex interplay is governed by the laws of electrodynamics and hydrodynamics. When we discuss the heating of plasma within the accretion disk, we are actually talking about magnetohydrodynamics, MHD, an exceptionally complex field of physics that details the behavior of a conductive fluid, or plasma, within a magnetic field. It is these specific processes, turbulence and magnetic reconnection, that are responsible for the immense energy transfer, culminating in the spectacular flare we observe. When analyzing the radiation spectrum, we delve into the realms of quantum mechanics and atomic physics. Different atoms and ions within the plasma emit and absorb light at distinct, predetermined wavelengths. This process creates a unique spectral fingerprint, allowing us to deduce the chemical composition, temperature, and density of the substance. A single flare at the galactic center thus becomes an unparalleled natural laboratory, providing us with a unique opportunity to test our fundamental theories under conditions utterly impossible to replicate here on Earth. We cannot synthesize a black hole in a laboratory, nor can we heat matter to tens of millions of degrees in an intense gravitational field. But we can observe nature performing these feats and meticulously compare the results with our theoretical predictions. Every time theory and observation align perfectly, it represents a triumph of the human intellect. But when they fail to align, that is arguably even better. It signifies that we are on the cusp of a major new discovery, a deeper, more complete physics. The flare from Sagittarius A-star, with all its inherent puzzles and discrepancies, may very well be the key that finally opens the door to this new realm of understanding. The mystery surrounding our central black hole is inextricably linked to the other great challenge in modern astronomy: dark matter. We know that the ordinary matter that makes up stars, planets, and even us accounts for only about 5% of the total mass energy of the universe. Roughly 27% more is comprised of mysterious dark matter. This matter doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational influence. Its existence is inferred from how its gravity affects the rapid rotation of galaxies and their movements within clusters. Galaxies spin so quickly that the visible mass alone isn't nearly enough to prevent them from tearing themselves apart. There must be something else, something unseen, that provides this missing gravitational force. And that, of course, is dark matter. Scientists believe that every galaxy, including our own Milky Way, is immersed in a vast spherical halo of dark matter. Crucially, the density of dark matter increases dramatically as you approach the galactic center. This means that right in the immediate vicinity of Sagittarius A-star, the concentration of dark matter should be at its absolute maximum. This proximity leads to several intriguing possibilities. First, dark matter particles might annihilate one another, producing pairs of standard model particles, such as high-energy gamma rays. some astronomers are actively searching for an excess of gamma-ray emission coming from the galactic center, an excess that cannot be explained by known astrophysical sources. While such an excess has been detected, its exact interpretation remains highly debated. Second, dark matter could potentially be captured by the black hole itself. While this process probably wouldn't produce the spectacular flares associated with swallowing normal matter, it could still significantly influence the black hole's mass growth over cosmic timescales. Finally, some speculative hypotheses suggest that the flares we observe might not be caused by a star falling into the hole, but rather by a dense clump, or a subhalo, of dark matter punching through the accretion disk. Though highly speculative, this idea illustrates just how intertwined the various cosmic mysteries truly are. By unraveling the secret behind the activity of Sagittarius A-star, we may simultaneously find the key to understanding the true nature of dark matter, arguably one of the greatest scientific puzzles of the 21st century. Let's take a moment to imagine this flare, not through the lens of scientific instruments, but as if we were watching it with our own eyes from a relatively safe distance. We wouldn't just see a single bright point. Instead, we would witness a distorted, truly surreal spectacle created entirely by gravitational lensing. The black hole's extreme gravity bends the path of light rays, acting like a cosmic lens. This means we wouldn't see just one image of the accretion disk, but several. We'd see a blindingly bright ring of light, the so-called photon ring, formed by light that has spiraled one or more times around the black hole before finally escaping its pull and traveling toward us. The accretion disk itself would appear dramatically asymmetrical. The section spinning toward us would look brighter and bluer due to the Doppler effect, while the receding side would appear dimmer and redder. And all of this would be rotating at a mind-boggling speed. Now picture the flare itself. A dazzlingly brilliant hotspot would erupt on the disk, the exact point where a chunk of matter plunged in. This spot wouldn't stay still. It would whirl along with the disk, gradually stretching out into an arc before eventually fading away. We would see its light reflecting off other parts of the disk, creating an intricate dance of light and shadow. If the flare were also launching a powerful jet, we'd witness two thin, fiercely brilliant streams of plasma erupting from the poles at the heart of this fiery carousel, stretching endlessly into the void. This vista, worthy of a surrealist master, isn't just a flight of fancy. It's exactly what our physical theories and computer simulations predict. When we collect data from telescopes, we are essentially trying to reconstruct this magnificent cosmic canvas from mere dots and lines on a graph. Modern visualization technology allows us to transform those dry numbers into thrilling images, making science not only comprehensible, but truly breathtaking. And perhaps in the not-too-distant future, the Event Horizon Telescope will allow us to capture not just a static image, but an entire movie of this dance on the edge of the abyss, playing out at the core of our Milky Way. The story of how we came to understand the center of our galaxy is filled with astonishing discoveries and the names of scientific giants. It all began in 1933 when radio engineer Carl Jansky, while investigating interference in radio communications, accidentally detected a powerful radio emission coming from the constellation Sagittarius. He didn't know what he was hearing, but he became the first person to truly hear the voice of the Milky Way's heart. Later, as radio astronomy advanced, this source was studied in detail and named Sagittarius A. In 1974, astronomers Bruce Ballack and Robert Brown found that this source was extremely compact and suggested it was linked to a central black hole. However, direct proof of its existence remained elusive. The real breakthrough came in the 1990s. The development of adaptive optics technology allowed ground-based telescopes to effectively see through the blurring effects of the Earth's atmosphere and capture sharp images of stars right at the galaxy's core. This is when the research groups led by Reinhard Genzel in Europe and Andrea Ghez in the United States began their decade-long marathon of tracking the orbits of these central stars. Their truly Herculean effort, spanning decades, finally paid off. They not only proved the existence of a supermassive black hole, but also measured its mass with incredible precision. In 2020, Genzel and Ghez, along with Roger Penrose, were awarded the Nobel Prize in Physics for this outstanding discovery. Today, we are witnessing a new era in the study of this object. While previous work focused on its static gravitational influence, we are now seeing it in action, in dynamic motion. The flare we are discussing, this particular event, connects decades of previous research and opens entirely new frontiers. We stand on the shoulders of giants like Jansky, Genzel and Ghez, continuing their work, peering ever deeper into one of the universe's greatest mysteries, one they helped us begin to unlock. Let's return to the menu of our galactic giant. We've already covered stars, gas clouds and asteroids, but there's another fascinating possibility we need to consider. Deep in the galactic core, alongside the stars themselves, we should find their remnants, white dwarfs, neutron stars, and stellar mass black holes. What happens when one of these compact objects is swallowed by this supermassive black hole? The merger of two black holes with vastly different masses is known as an extreme mass ratio inspiral. If a stellar mass black hole, say 10 times the mass of the Sun, plunges into the supermassive hole, 4 million solar masses, it won't cause a bright electromagnetic flare simply because it has no matter to form an accretion disk. However, this event generates an incredibly powerful burst of gravitational waves. These waves, ripples in the very fabric of space-time, then spread across the universe at the speed of light. Current detectors like LIGO and Virgo aren't yet sensitive enough to register these events from the center of our own galaxy, but future space observatories, such as LISA, definitely will be. The picture changes entirely, however, if a neutron star falls into the black hole. A neutron star, although extremely compact, is still made of matter, superdense neutron matter. Before the final plunge, tidal forces will rip it apart, and a portion of that shredded material will form a small yet incredibly hot and bright accretion disk. This results in a brief but tremendously powerful flash of gamma rays and X-rays alongside a burst of gravitational waves. This scenario, known simply as a black hole neutron star merger, is a fantastic fit for explaining the observed flare, accounting for both its brevity and immense power. What's more, these events are considered primary factories for forging the universe's heaviest elements, including gold and platinum. So perhaps by observing this flare, we weren't just witnessing an act of cosmic cannibalism, but also the very moment that precious metals were forged, metals that will eventually find their way into new stars and planets. It just goes to show how interconnected the universe is. The death of one object can truly mark the genesis of something entirely new. Throughout this lecture, we've touched upon various types of telescopes operating across the electromagnetic spectrum. Now let's pull all this information together to truly appreciate the complexity of modern astronomical research. This approach is known as multi-wavelength astronomy, and it's the key to unlocking complex phenomena. It all started with radio waves. Radio telescopes like the VLA in New Mexico or the Global Event Horizon Telescope Network allow us to peer into the very heart of the accretion disk and resolve structures the size of the black hole itself. They are sensitive to synchrotron radiation, which is emitted by electrons spiraling within intense magnetic fields. Next, we have infrared telescopes, both ground-based, such as the Keck observatories in Hawaii, and space-based, like the James Webb Space Telescope. These instruments allow us to see straight through obscuring dust, monitor the movement of stars orbiting the black hole, and study the cooler gas and dust within the accretion disk. Visible light, however, barely reaches us. This is due to the thick clouds of dust and gas lying between us and the galactic center. Consequently, the optical range gives us very little insight. But when we shift to higher energy wavelengths, the picture brightens considerably. X-ray space observatories, such as Chandra, XMM Newton, and NuSTAR, are our primary tools for studying flares and outbursts. They observe the hot plasma in the accretion disk, heated to millions of degrees. In fact, these instruments are precisely what detected the recent awakening of our galactic giant. Finally, gamma-ray telescopes like Fermi and HESS register the highest energy photons. They allow us to study particle acceleration processes reaching relativistic speeds, potential relativistic jets, and of course, the famous Fermi Bubbles themselves. Only by synthesizing the data from all these instruments can scientists construct a complete picture of an event. Radio tells us about magnetic fields, infrared shows us the stars, X-rays reveal the hot plasma, and gamma rays expose the most extreme processes. It's much like how doctors use multiple diagnostic tools, X-rays, ultrasounds, and MRIs to form an accurate diagnosis. In astronomy, the principle is identical. To truly understand a cosmic organism, we need to observe it across every color of the electromagnetic spectrum. As we wrap up our exploration of the Milky Way's heart, I want to take a moment to emphasize just how unique our current situation is. We aren't just living in an age of great astronomical discovery, we are living in an era where those discoveries are accessible to almost everyone. Just a few decades ago, telescope data was the exclusive domain of a small circle of professional astronomers. Today, numerous observatories release their raw data into the public domain. Anyone with the necessary knowledge and enthusiasm can download this data and conduct their own research. Citizen science projects like Galaxy Zoo are engaging hundreds of thousands of volunteers globally to classify galaxies and hunt for new celestial bodies. This means the line between professional and amateur science is blurring rapidly. The next major breakthrough might not come from a seasoned, grey-haired professor, but from a high school student in a small town, or a retiree who just discovered a passion for astronomy. What's more, the topic of space itself is exploding in popularity. Pop science lectures, YouTube channels, and podcasts, all of these platforms are making complex scientific concepts accessible and understandable to a massive audience. Our lecture today is a vital part of this global movement. By sharing this knowledge, we aren't just reciting interesting facts. We are sharing the sheer thrill of understanding the cosmos. We aim to show that science isn't about dry formulas in textbooks. It's a thrilling detective investigation full of mysteries, unexpected twists, and breathtaking moments of realization. And the flare of Sagittarius A-star is one of the most intriguing chapters in that endless book. Who knows, perhaps after hearing this lecture, some of you will be inspired to learn more, pick up a book on astronomy, or maybe even dedicate your lives to science. If so, that would be the greatest possible outcome. Because the more people who look up at the sky with genuine curiosity and understanding, the better humanity's chances are of solving the greatest mysteries of existence. Let's circle back to the central question. What exactly did the black hole swallow? Despite everything we know, we still don't have a definitive answer. Each hypothesis has its pros and cons. The stellar tidal disruption hypothesis nicely explains the immense energy output, but it clashes with the short duration of the flare. A classic stellar disruption event should have lasted for months. To salvage this idea, we have to assume either that the consumed star was extremely small and dense, or that what we observed was not the disruption itself, but some secondary, shorter-lived effect. The second hypothesis, involving a falling gas cloud, perhaps a remnant of the G2 object, fits the short flare duration perfectly. But this raises a different question. Could a cloud of gas, even a dense one, generate that much energy? Calculations suggest it's possible, but only barely. The cloud would have needed to be extremely massive and strike the accretion disk at a precise angle. The hypothesis that an asteroid or a large comet fell in is quite attractive. It neatly explains both the brevity and the power of the flare. The difficulty here is that we simply don't know how many large objects like that are orbiting the galactic center. Is this a regular occurrence or an extremely rare exception? Finally, exotic scenarios, such as a merger with a neutron star, are physically compelling, but they require an even rarer alignment of circumstances. The probability of such an event is incredibly low. This uncertainty is not a sign of scientific weakness. On the contrary, it demonstrates its integrity. Scientists are deliberately holding back from making hasty conclusions. They continue to collect data, build models, and test hypotheses. We might find the answer when we detect the next flare and are able to compare it directly to the previous one. If the flares are similar, that would point towards a regular process, such as the predictable infall of asteroids from a hypothetical belt orbiting the black hole. If, however, they are entirely different, that would strongly favor random singular events, like the absorption of stars or gas clouds. Either way, this mystery will continue to captivate astronomers for years to come, and we eagerly await new data from the very heart of our Milky Way. Beyond pure fundamental research, studying extreme objects like Sagittarius A-star has highly practical implications. It serves as a powerful driver for technological advancement. Capturing an image of the black hole's shadow required more than just linking telescopes across the globe. It necessitated the development of novel data processing methods, new algorithms, and the creation of ultra-precise atomic clocks to synchronize observations. These technologies subsequently find applications in countless other fields, ranging from medicine to communication systems. To analyze the enormous flood of data streaming in from these telescopes, we are advancing methods in machine learning and artificial intelligence. Neural networks are being trained to locate weak signals within the data, classify objects, and even predict astronomical events. These very same algorithms are then utilized for pattern recognition, analyzing volatile financial markets, or diagnosing complex diseases. Furthermore, the development of new X-ray and gamma-ray detectors, capable of catching individual photons and precisely measuring their energy, is driving the creation of more sophisticated medical scanners and advanced security systems. Thus, by gazing into the deepest reaches of space, we are not just satisfying our inherent curiosity, we are actively propelling all technological progress forward. Investments in fundamental science, which some people might view as a wasteful expenditure, are in reality crucial investments in our collective future. No one can predict which of today's astronomical breakthroughs will lead to the life-changing technologies of tomorrow. When Carl Jansky first detected radio waves emanating from space back in the 1930s, he could never have imagined that this discovery would launch the entire field of radio astronomy. This led to the detection of quasars, pulsars, and ultimately the creation of the Global Positioning System, or GPS. Crucially, GPS relies on tiny corrections derived from Einstein's general theory of relativity, a theory rigorously tested using these very same cosmic objects. The history of science is filled with such examples, and there is no doubt that studying the awakening of this ancient object at the center of our galaxy will also yield its own unexpected and beneficial results. Our journey to the heart of the Milky Way is drawing to a close. It began with a single signal, a mysterious flash detected by our telescopes. Yet that initial data led us to contemplate the most fundamental questions: the nature of gravity, the ultimate fate of the universe, and our own place within it. We have seen that the core of our galaxy is far more than just a point in the night sky. It is a complex, dynamic system governed by the most extreme laws of physics. We came to know its ruler, the supermassive black hole Sagittarius A-star or A-star. It can shift between being a quiet sleeping giant and a raging violent monster capable of shaping the destiny of the entire galaxy. We recognized that its recent awakening was not an anomaly, but merely a fleeting moment in this object's long, turbulent existence. It is an echo of its powerful past and, potentially, a glimpse of its future. We've also witnessed how modern science truly works. It is not the pursuit of a few individuals, but the collective effort of thousands of people across the globe. It is the careful synthesis of observations gathered using our most sophisticated instruments, combined with theoretical models forged by the power of the human mind. It is a continuous process of generating hypotheses, rigorously testing them, and, if necessary, abandoning them in favor of new, more precise understandings. This story is far from over. The major breakthroughs, in all likelihood, are still ahead of us. New telescopes, novel methods of data analysis, and fresh theoretical insights will allow us to peer even deeper into the mysteries at the Milky Way's heart. And whatever we discover there, one thing is certain: it will be astonishing, because the universe consistently proves itself to be stranger, more complex, and more beautiful than we could ever imagine. The chance to reach out and touch these mysteries, even across a distance of 26,000 light-years, is one of the greatest gifts we possess. Thank you for sharing this journey with me. All right, let's wrap up our cosmic investigation. Right at the heart of our galaxy, 26,000 light-years away, a sleeping giant, the supermassive black hole Sagittarius A-star, suddenly woke up. It produced an X-ray flare hundreds of times more powerful than anything we had ever observed from it before. This event was a true gift for astronomers, offering an unprecedented look into the most extreme conditions in the universe. Analysis of this cosmic scream and the light echoes reflecting off the surrounding gas clouds revealed that our giant hasn't always been so dormant. In the past, it experienced periods of much higher activity, traces of which we still see today in the form of the gigantic Fermi Bubbles towering above the galactic plane. We examined the main suspects for the black hole's recent meal, everything from a star being shredded apart to a common gas cloud, or even an exotic merger involving a neutron star. While we don't have a final answer yet, the very process of this scientific detective work has showcased the sheer power and beauty of modern astrophysics. This event isn't just a local firework display, it's part of a global feedback loop where the central black hole influences its entire galaxy, regulating the birth of new stars and shaping its ultimate appearance. We live in a unique era where technology like the Event Horizon Telescope allows us not just to theorize about black holes, but to literally observe their shadows. And every new flare offers us another chance to learn more, test our boldest theories, and inch closer to solving one of nature's greatest mysteries. Thank you so much for spending this time with us, diving deep into the secrets of the cosmos. If you enjoyed this sleep lecture and want more cosmic journeys like this, please make sure to subscribe and hit that notification bell so you don't miss a thing. Give this video a like as it greatly helps promote science. And now I have a question for you. What do you think really happened at the center of the Milky Way? Which theory seems most convincing to you? Or perhaps you have your own entirely new hypothesis? Share your thoughts in the comments below. We'd love to read and discuss them. Good night and clear skies.